Okay, so this video is going to be going over basic gas laws. So really the combined laws and then also the laws that make up the combined law, and then also the ideal gas law. So before we really talk about those laws, there are three main variables when we talk about gases. The temperature, the volume, and the pressure, and all of those things are related with the gas. So if you change the variable of one of those, that actually can impact the volume and the temperature of the gas. So with pressure, you're going to see lots of different units. You're going to see ATMs, millimeters of mercury, torrs, kilopascals, also sometimes bars, but that's typically not used. So 1 ATM is equal to all of these. So this is just one of those things, you really just need to know these. So 1 ATM is equal to 760 millimeters of mercury. It's also equal to the same amount of torr, and then 101.325 kilopascals. All right, so if we want to make a simple conversion, we have 657 millimeters of mercury. We want to convert that to atmospheres, so atmospheres will go on top, millimeters of mercury on the bottom, and it's equal to 760, so it's just this divided by 760. It's a little bit less than 1 ATM. So it's 0.86447. Okay, so about 0.8464 ATMs. So same thing right here, 830 torr. If I convert that to ATMs, 1 ATM is also equal to 760 torr. So just divide this by 760, so you're going to get a little bit more than 1 ATM. So you should get 1.09 ATM for this. All right, so this is just something you need to know. You need to know these conversion factors because I don't believe they're given to you on the reference sheet. So you just have to know them. All right, so when we measure pressure, that can be either done with a barometer or a manometer. A barometer measures the atmospheric pressure. So this is for the atmosphere. So when you're sitting in a room or when you're outside, the pressure that you feel being exerted from the atmosphere. A manometer can measure the pressure inside of a container. So if you have got a gas inside of a container, those molecules are banging against the sides of the container, so they will create pressure inside that container, and that can be measured with a manometer. So the way this works usually is that you have some sort of U-tube with some sort of liquid. It used to be mercury. It's not made with mercury anymore, but you have some sort of tube, and if you're going to measure the inside of a container, so you're going to have the gas inside of some container. It's going to be attached to some tube with a liquid. And you're going to have two competing gases. You're going to have the gas inside the container, and then you're also going to have the atmospheric pressure. So the atmospheric pressure is going to push down on this liquid in this tube, and then the gas inside of the vessel, or whatever the container is, will also push down on the liquid. Well, that difference is equal to the pressure of that gas. So you're either going to add the atmospheric pressure to that difference, or you're going to subtract it. It just depends on what's happening with this tube. All right, this is just another picture of a device used to measure, and this is a barometer, so this is going to measure the air pressure in the atmosphere. So basically the air will press down on this liquid and then force it up into this tube, and then that can tell us what the air pressure is equal to. And there will be nothing inside of this tube. It'll be a vacuum essentially. All right, so KMT is kinetico molecular theory, and basically this is the theory of moving particles. So in an ideal situation, gases would behave like this. So this is with ideal situations. Gas particles are always in constant random motion. So whenever you have a gas, those particles are constantly moving, and they will move in a straight line until they hit something and then move in a different direction. The volume of the particles is negligible. So basically they say that there is no volume when you have a gas. That's not necessarily true. It's just if you compare the space that the particles of a gas take up compared to the container that they're in, it's very, very small compared to that. So we say that it's negligible. Also, that the attractive repulsive forces between the particles are negligible. So you've got these particles that are moving very far apart from each other, and really there should be no attraction or repulsion with those molecules. They're just moving all over the place. It's almost like they're not interacting with each other. The collisions are also elastic, which means that the energy is not lost when you collide. An inelastic collision, so in elastic, would be where energy is not necessarily conserved. All right, so the average kinetic energy of the particles is also proportional to the temperature. So basically, as your temperature increases, so does your kinetic energy. So if you increase the temperature, you're going to increase the kinetic energy, which is the energy of moving particles or movement. Okay, so the first gas law I'm going to talk about is Boyle's law. Boyle's law deals with volume and pressure. So volume and pressure are inversely related. So if you remember, that means that as one goes up, the other one goes down. So as pressure or volume goes up, the other variable will go down. So the easiest way to think about this is to think about a syringe with a little pump. So basically, as you push down on this, you're going to increase the pressure, and basically you decrease the space that the gas has. So as I increase the pressure, the volume decreases, and that's what you're going to see in this graph. So you have volume on the y-axis and pressure on the x-axis. So when you see this, this means as volume is increasing, so as it gets higher and higher, so as our volume goes up and up, our pressure decreases, okay? And basically that makes sense. If you have more space for the particles, you're having less collisions. So as you increase your pressure here, you're going to see that your volume is getting smaller and smaller. But it's never going to actually hit zero. It's going to always be approaching zero, but it's never going to hit zero because all matter takes up some space. Now, if I were to take the volume of a gas and multiply by that pressure at that volume, I'm going to get a constant. I'm going to get a value that's always the same. So it doesn't matter what the pressure is. If I take the pressure and I multiply it by the volume at that pressure, I'm going to get the same number, which really means that if I take an initial pressure and an initial volume, multiply them together, I should get the same number if I take a new pressure and multiply it by the new volume. So this is Boyle's law right here. And the 1 would be initial, the 2 would be the final. So if I change one variable, I can figure out what the other variable will be. Also, if you look at this graph, this is an inverse relationship. So if you take this data and take the inverse of the pressure, so 1 over p, if I take all of these data points and then just divide it, I take the inverse of it, so 1 divided by that number, what I'm going to get is a line that looks like this. Okay, so that's true of any inverse relationship. You're going to get a straight line if you take the inverse of it. Okay, so Charles's law deals with volume and temperature. So if you increase the temperature, the volume increases. If you decrease the temperature, the volume decreases. So think about a balloon. If you were to freeze a balloon, those molecules would actually start to move closer and closer together, so the volume would get smaller and smaller. And really what you're doing is you're taking away kinetic energy, so they're not moving as much. So the volume, or the amount of space that they take up, is smaller if you decrease the temperature. Same is true if you increase it, or your volume would increase. Now, if you were to take the volume of any gas and divide it by the temperature at that volume, you're going to get a constant. So that means you can do the same thing. You can take the volume of any gas divided by the temperature of that volume, and you can set that equal to a new volume divided by its temperature. So I could figure out what my new volume or temperature should be if I change a variable. But I don't like having fractions like this. It's harder to calculate problems. So what I do is I convert it into something that looks like this. So if you've got this, you can basically multiply it out. So I'm going to take this, multiply T2 out, and then multiply T1 out. And this is what I'm going to get. And this is much easier to work with than this. So anytime that you have an equation like this, just go ahead and rearrange it to look like this. Okay, so this is what a direct relationship looks like. So if it's directly related or proportional, this is the kind of graph you're going to see. And again, volume here is on the y-axis, temperatures on the x. Okay, Avogadro's law deals with moles and volume. So if you increase the amount of your gas, you increase the volume or the space that it takes up. And that makes sense. So if I take the volume of that gas and divide it by the amount of the gas, I'm going to get a constant. So of course I can get another equation for it. Okay, so if I graph this, well, I should see a direct relationship, so it should be a straight line. And again, volume is on the y-axis, and then amount or number of moles will be here. All right, so Gay-Lussac's law. You have pressure and temperature, and they are also proportional. So if you increase the temperature, you increase the pressure. So think about it this way. If you increase the temperature, you're going to increase the kinetic energy, and that's going to keep the molecules moving. They're going to start colliding more and more and more, which increases the pressure. So again, you can take the pressure of any gas divided by that temperature at that temperature and get a constant. So you have another equation. And you should have a direct relationship, so it should be like a straight line. And here pressure will be here, and then temperature will be on the x-axis. Now, I could take all of those laws and make one convenient equation. I like one equation. I don't like having to know a bunch of different equations. So if you take all of those variables together, you get this equation. And of course, I do not like that there are fractions involved, so I rearrange it to look like this. So really, your pressures and your volume will be the same number, but your temperature and your number of moles will be different numbers, so they're reversed. Okay, so if you're solving for a new pressure, volume, amount, or temperature, so if a variable changes, you use this equation. And then if it doesn't list any of the variables, or if it says that it's constant, you just take it out of the equation. You don't worry about it. So if the pressure is being held constant, or if the amount of gas is being held constant, you can just take that variable out of the equation. So let's look at an example. I have a gas at 25 degrees Celsius in a closed container and has its pressure raised from 150 to 160 ATMs. So what is the final temperature of the gas in Celsius? Okay, this is something you probably need to write down if you haven't written this down or you don't remember this. When we're dealing with gases, temperature is always in Kelvin. You have to have it in Kelvin, otherwise it's not going to work. Kelvin does not have a negative value, so that means you can use it for gas law, or for gas laws. Come on, Zeus. All right, so first thing you do, pull out all of the variables. So figure out what was given to you in the problem and what you're looking for. So it says a gas at 25 degrees Celsius. So I have a temperature. And it looks like I'm looking for the original, or I'm looking for the new temperature. Okay, so I'm looking for the new temperature right here, the final temperature. So I have the initial temperature here. It also says that it has its pressure raised from 150 to 160. So 150 ATMs would be my initial pressure, because that's the first one. And my new pressure will be 160. I'm looking for the new temperature. So I know that a variable has changed here, pressure, volume, temperature. If any of those things change, you're using combined gas law. All right, so here's my equation. Now, it doesn't tell me anything about the volume or the amount, but really it's in a closed container. So if it's in a closed container, I can assume the volume's not going to change. So that's going to be constant. I can take it out of the equation. I don't need to worry about it. Also, no gas is being added or released, so I can also not worry about the amount or the number of moles. So really my equation is this. So if anything is constant, I just take it out. All right, so now before I can do any calculations, this has to be in Kelvin, so you're going to add 273 to do that. So anytime that you have a temperature, it has to be in Kelvin. It has to be. You cannot forget to do that. All right, so now I'm just going to plug it in the equation. So 150 is my P1. T2 is unknown. P2 is 160, and then T1 is 298. Make sure you pick the right temperature here. All right, so I'm going to multiply these out. I get 47,000. Divide out my 150. So my T2 would be 317.86. And this is going to be Kelvin here, but the problem is asking for Celsius. So I'm going to take my temperature of 317, and then I'm going to subtract 273. And then that's going to give me my new temperature in Celsius. So it's 44.8 or 45 degrees Celsius if I round to sig figs. All right, so let's look at another one. All right, a gas has a volume of 0.572 liters at 35 degrees Celsius and 1 atmosphere of pressure. What is the temperature inside the container where this gas has a volume of 0.35 liters at 1 atm? So pull out your variables. It says a gas has a volume of 0.572 at this temperature. So the temperature is 35 degrees Celsius, and it also has a pressure of 1 atm here. Okay, so all of these variables happen at the same time. So basically, this volume goes with this temperature, goes with this pressure. So I could really just assign it a 1 or a 2. As long as you keep them together and assign them the same number, it's fine. But it is the initial temperature, volume, and pressure. So I want to know what the new temperature is inside of a container where the volume is 0.35 liters and the pressure is 1.0 atm. All right, so I have a variable that's changing, so I know it's ideal gas law. Here's my equation. All right, so when I look at this, I know that I've got to convert this into Kelvin, so that's 308. So 35 plus 273 gives me 308 Kelvin. So now I can plug it into the equation. Well, actually, if I'm looking at this, okay, it doesn't talk about the gas being released or gas being added, so I can take out amount. And also, pressure stays the same, so I can just take that out too. It's not changing, it's being held constant, so really I'm just looking at volume and temperature. All right, so now I can just plug it in the equation. So as long as your liters match, you can just plug it in. If it was milliliters and milliliters, then you could just leave it and plug that in as well. So volume 1 is 0.572. T2 is unknown. V2 is 0.355. And T1 is 308. All right, so you're going to multiply this out. You get 164.78. All right, so T2 is going to be equal to 288 Kelvin. And it doesn't specify here if it needs to be in Celsius or Kelvin, so we'll just leave it like that. That's fine. All right, so the second real law that you really need to know is the ideal gas law. So the combined gas law has Boyle's law, Charles' law, Gay-Lussac's law, and Avogadro's law combined in there. Really, you just need to know those relationships. The ideal gas law is another equation, and this one will be given to you on the test. And it's PV equals nRT. Now, R is the universal gas constant, and it's equal to 0.0821 liters atmospheres divided by moles and kelvins. And there's actually another R that you could use that involves different units, but these are the main units that we use. So, and both of our values are given to you. Okay, so you don't have to memorize this. Temperature is still always going to be in kelvins here. All right, so let's look at an example. All right, so when you look at the ideal gas law, you're going to use the ideal gas law when nothing is changing. So if you're just looking for a variable, you use PV equals nRT. So you're going to use PV equals nRT as long as nothing is changing. If something is changing, you use the combined gas law. All right, so what volume? So we're looking for a volume here. Would 32 grams of NO2 be equal to? So if they give you 32 grams, that more than likely is going to be your N, or your amount. So N is going to be your number of moles, but we can get moles from grams. All right, so it also tells us that our pressure is 3.12 atmospheres, and that our temperature is equal to 18 degrees Celsius. All right, so I'm just looking for a variable here. Nothing is changing, so I know I'm going to be using the ideal gas law, PV equals nRT. So if I look at R is a constant. It's always this number. I have to make sure all my units match R. As soon as they match, then I can plug it in the equation. So first thing, let's convert this into moles. So 1 mole is equal to so many grams, and it's 46 grams for NO2. And that is going to give me 0.696. 6 moles, okay. So I was given a pressure in atmospheres. Atmospheres and atmospheres, it matches, so I don't have to worry about that. Temperature has to be in Kelvin regardless, so add 273 to that. And you're going to get 291. So then you can just simply plug it into the formula at this point. So P is 3.12. V is unknown. N is 0.696. R is 0.0821. And my temperature is 291. All right, so if I multiply it all out, I get 16.6 here. Then divide it out, and you're going to get 5.33 liters. And you're going to keep it at 3 sig figs because you've got 3 sig figs in all your measurements. All right, so remember, if nothing changes with the gas, you're going to use this. And then if something changes, you use the combined gas law.